Let's see how does the substrate affect the rate of its SN2 reaction. If we think about, in general, the structure of this halide, then this leaving group serves two functions. The first one is polarize the carbon to make it delta positive, right? And the second one is to leave, and importantly, with the electron pair. And the leaving group facilitates both the attack and its own expulsion in a way. And so a good leaving group needs to be electron withdrawing. Because that way it will make the carbon positive enough to be susceptible to the nucleophilic attack. And good groups to do that are based on chlorine or oxygen, or even elements that are not that electronegative, such as sulfur, provided the proper substitution has been achieved on nitrogen. Okay? The second criterion that a good leaving group might satisfy is it must be stable once it has already left. What does this mean? Well, it means that once we perform our SN2 reaction, such as this one, we will generate the free leaving group, H2O. And this thing must be a stable molecule, as it is in this case. Because a stable molecule will not will drive the reaction in the direction of its formation. Unlike the unstable molecules, which is the case here, where we have the substitution of pure methanol, which then generates methyl bromide, but also generates the hydroxide anion, which is unstable. And hydroxide anion is unstable because it is a base, so it will desire to annihilate its own negative charge by reaction with the proton, or something else which has delta plus charge. In other words, good leaving group cannot be a good base. So a good leaving group must be a weak base. And we see that with water as an example of a weak base. Okay? And in general, good leaving groups are either neutral molecules, such as water, ammonia, alcohols, phosphines, etc., or stable anions. So stable, very weakly basic anions, such as I- or Br- or RsO3-, which is stabilized extensively by resonance, or things like acetate, which is also extensively stabilized by resonance. The good thing is that, as we've seen in the case of methanol, we can convert oftentimes a poor leaving group, such as OH group, into a good leaving group, such as OH2 group, through protonation. And so once we convert the poor leaving group into something that can leave as a neutral molecule, then that facilitates the SN2 reaction significantly. The third factor doesn't have much to do with the leaving group, but rather with what the leaving group is attached to. So this is the steric bulk. And we can see that easily if you compare the reactions of methyl substrates, which occur at a relative rate of 10, versus the primary ones, which are about 20 times slower, secondary ones, which are about 50 times slower than the primary ones, and then the tertiary ones, which are about 1,000,000 times slower than the methyl substrate. And the reason for this is pretty straightforward. If we have 3 methyl groups attached to the central carbon, then this will be a p-butyl group, and our nucleophile will have a very hard time squeezing in here and approaching carbon, so it simply blocks the attack. So the tertiary substrates don't work in SN2. And the secondary substrates are already slow. So it's really the SN2 reactions that are best for metal substrates or for primary substrates. The word of caution, though, we have to look at all these systems in perspective. So sometimes we can have, in principle, a primary substituent, such as in this case with this neopentyl group. And even though this is primary, but still it is still blocked by the neighboring tertiary T-butyl group. And in such cases, even the primary substrate will not react almost at all. However, these cases are rare because it's sort of a tweaked situation. So a good general rule of thumb for substrate effects: we need a good leaving group, which must be electron-withdrawing, has to be a weak base, and we need the substrate, which is either primary or metal substrate. If we have a secondary substrate, we can sometimes get away with it. Tertiary substrates simply do not undergo SN2 reactions.